So, dear ladies and gentlemen, our next talk is from Hendricks from the National Institute of Standards and Technology, better called as NIST, from the United States of America. Very welcome.
Thank you.
And you will talk about the NIST-on-a-Chip, and I'm very interested about what is new. So it's yours. Please.
Okay, thank you. Thank you so much. I'm very pleased to be here and tell you about some really exciting stuff that's going on in the measurement science world. It's really great to be here at a conference where there's so many people who are passionate about metrology and measurement. So it really does bring quite a bit of joy. Okay, so the outline for today. I'm going to talk a little bit about the NIST-on-a-Chip program. I do have a short video at the beginning, and then towards the end I have about a 2 or 3 minute video that you're going to see that talks about high-risk research and the importance of quantum-based standards. Let's see. So I don't have to preach too much to this audience about why we care about standards, but I always like to put some real-world applications in there. So I'll talk a little bit about the importance of sensors, for example, in airplane travel. And I'm going to take a little mini deep dive into some of the technologies that we're working to move from laboratory scale to sort of benchtop scale. And we like to envision that this could happen fairly quickly, get it to sort of sensor scale that you could actually wind up seeing on a vendor table at a show like this. So that's my outline, and I'll just briefly mention at the end sort of what does this mean for a National Metrology Institute like NIST or PTB when you've got these sensors that are self-calibrating. How do you do the quality assurance on such a system? So, and that's a teaser if you stick around. Now, if you were by yesterday, I gave a very similar talk. However, today I've got some new slides in there that are based on the quantum technologies. Okay, so I come from NIST in Gaithersburg, Maryland. NIST actually has 2 campuses, one near Washington, D.C., where I come from, and the second one is in Boulder, Colorado. And it's Boulder, Colorado that actually has the atomic clock, but there's a lot of exciting stuff in the NOAC program going on in both campuses. If you go to our NIST website, you'll see that NIST is engaged not only in metrology and metrology activities, but we also pride ourselves in doing a variety of groundbreaking research. In terms of our metrology capabilities, if you go to the NIST website, you can find a variety of calibration measurements being offered. We also offer custom calibration solutions. So if you have a particular type of gauge that needs unique testing, we will do that. As Siegfried mentioned in his talk earlier this morning, NIST doesn't do a whole lot of calibrations. It's in the thousands. It's not hundreds of thousands or anything like that, because we're just doing the highest level calibrations of a chain, and it's that calibration chain that brings everything down to the instrumentation that you find at a trade show like this. Okay, so here's where I'm going to cue the video. So if our audio guys are ready, I'm going to press play.
Technology has changed over the years. It has gotten smaller, more affordable, more mobile. These advances demand a new era of measurement science. Introducing NIST-on-a-Chip. These devices will combine the latest advances in metrology with the latest advances in technology. They will make the most precise measurements in the world smaller, affordable, and most important, based on quantum standards NIST has pioneered for decades. You will be able to take NIST with you, anywhere, at any time. It's up to you where these devices will go and what new frontiers they will allow us to explore. Partner with us and be part technology revolution.
Okay. So as you can see from that, this is a pretty audacious challenge. We're talking about getting sensor technologies eventually into your phone. In the video, is it science fiction? Some of it. But I'm here to try and convince you that this is really happening, and we're taking steps to make it happen. Okay. So as you can tell from the video, what we're really trying to do is figure out how to use nature to become our sort of calibration in the sky, if it was to be thought of that way. So nature is very reproducible in terms of what it does. So if you can observe those quantities very directly, the idea is that now nature is your standard, and it's going to enable us to basically get to sensors when they use this that are calibration free, in the sense that they don't need to be sent back through this calibration chain. And if they can be made small and manufacturable, that's sort of where getting into your phone comes from. If things get smaller, they also get cheaper. So affordability is a super important part of this. If everything is really expensive, then no one will use it. But when we see this all coming together, we really do see this capability of taking these measurements that are kind of locked up at NIST and putting them right out there in the hands of the everyday user. All right. So for the examples, if you've flown on an airplane recently, you probably know that the airplane is actually a very complicated system, and that those systems actually do need to be calibrated on a regular basis to ensure that they're going to operate safely. Some of those systems may be not so critical, but in the case of flying, it turns out that just about everything is critical, because if something goes wrong at 30,000 feet, it can be catastrophic. In fact, I was at this show last year, and we had a speaker from Airbus, and he was talking about the heating and air conditioning on a modern Airbus. You would think, air conditioning system? Not that complicated. This is an X-ray showing all the ductwork and electrical wires and so on that are going on sort of underneath the skin of an airplane. When you get on an airplane, you're just seeing seats and so on, but really the entire plane is loaded with technology and sensors. And in this particular case, the heating and air conditioning, you would think, not that important, right? So what if it gets a little bit cold? Well, it also controls the pressure inside the plane. And if you're going up in altitude and you don't do something about the amount of total pressure in the cabin, of course, the passengers will lose consciousness due to not having enough oxygen. This is really a problem if it's the pilot, and it's certainly a problem if you're a passenger as well, because, with a weak heart or something like that, it could be fatal. Worse yet, if this pressure control system fails, it would actually be possible to exceed the mechanical limits of the plane and cause it to, burst like a balloon. And when you descend back down in altitude, if you don't repressurize the plane adequately as you're going down, you can actually cause a crumple or implosion of the air skin. So very important that things like your pressure sensors that are controlling your airflow for your plane are operating, and that the valves and switches and so on and so forth are operating also in a very precise way. Okay, so measurements are, I think, safe to say this audience is well aware, pretty much used every day in our manufacturing. And in the United States, when we went and asked our economic folks, they say, well, what is the impact of the measurement chain? A lot of the measurements that go on at NIST, again, these are thousands of measurements, but they go out into our economy, which is responsible for about $14 trillion in GDP. So that's where you can see the importance of metrology in terms of what it does to our economy. The NIST is actually in the Department Department of Commerce in the United States. And so it's understood that metrology and measurement and legal metrology, which we heard about today, are incredibly important to how that economy functions. And passing those calibration chains along is what we heard about in terms of these digital calibration certificates. Also very important, and I'll just add a note here, I do see as a vision to the future that any sort of NIST-on-a-Chip device would also carry along some kind of digital certificate with it that would talk about how it could be used, when it could be used, what its lifespan is expected to be used, and so on, because this has become critical in the role of how do you maintain a calibration chain where you're not actually returning things back and having them tested. Okay, so now I'm going to talk a little bit about standards. So in this particular case, I'm going to talk about time. So in this simple example, if you have one clock, you know exactly what time it is. Well, what happens when you get a second clock? Now maybe you're not so sure. There's some uncertainty here, and if that uncertainty isn't a problem for you, then maybe it's okay that you are 5 minutes off. If you're planning on catching the train exactly at the minute, then maybe this is a problem. You want your clock to be a little bit more accurate. If, however, you're just looking at, say, the agricultural seasons to grow crops, then here's a clock that might actually work pretty well for you. So in this case, we're talking about Stonehenge. It is not very accurate in terms of seconds or minutes or even hours, but it is very accurate in terms of what day it is. And with that knowledge, it was very important and very useful. We call this fit-for-purpose metrology. And it's something that I think the folks at the NMI sometimes forget. It's not always about shaving off another zero and making it more accurate. It's making the device that you're using fit for the application that you're going to use it in. In this case, Stonehenge works incredibly well. Evolution of clock technology. This is a very quick evolution I'm going to give here. We get to maybe the 1700s, and we have the mechanized age with gears. This gets us down to clocks that can keep on the order of seconds a day. This is pretty impressive in terms of the evolution of clocks. A big change happens with the quartz crystal oscillator. I was somebody in the 80s that had one of those little digital watches that was amazing because you could also do calculations on it as well as tell the time. This little quartz oscillator is good to a fraction or a few milliseconds a day. So even better, and what's really powerful about it, today it costs maybe 25 cents to make a timepiece with that kind of accuracy. Fast forwarding again is the chip scale atomic clock. So I mentioned in Boulder, we have a lab scale experiment with a fountain atomic clock that will have the accuracy of a part in 10 to the 18th. And let me just say that again, a part in 10 to the 18th. That is so accurate that it can tell the difference in aging between your head and your feet due to the dilation of time due to the gravity of the Earth's field. And to me, that's just amazing. Now, shown here on this slide is a chip-scale atomic clock. This was actually developed based on DARPA, which is a defense organization in the United States. They were very interested. They invested about $100 million in this. And what they got is an atomic clock that's a little bit bigger than a deck of cards that can now go into a piece of electronics. And that electronics can go on critical applications. Some of those applications include cell phone towers. As you make a call, your call goes out. It may be picked up by more than one tower, and each of those packets gets encoded with a timestamp and gets sent and then reassembled. So even fractions of milliseconds or microseconds, or even worse, nanoseconds, could matter when all these packets are assembled. And so a lot of timing is done with GPS, but the problem with GPS is sometimes you lose lock, and an atomic clock can do what's called timing holdover. It keeps everything running at the right thing until GPS signal is reestablished, and then the clock, what's really amazing about this chip scale clock, it actually reacquires GPS and can recalibrate itself to UTC in an instant once GPS is restored. So it's an example of something that you put out in the field, you don't need to calibrate it. This isn't science fiction, this is happening now. Okay, so we're almost because, well, actually, we're just past the 5-year anniversary of the redefinition of units. If you missed this, well, okay, let me tell you a little bit about it. If you haven't, I'll go through this fairly quickly. But essentially what happened is that we went from an artifact-based system for things such as the triple point of water for measurement of temperature, and the kilogram for measurements of mass. And the kilogram is shown up here is the metal, platinum iridium lump of metal that's in those glass jars that's held at the BIPM just outside of Paris, France. And what's amazing is that 5 years ago, we actually said, no, we're not going to use a lump of metal anymore. We're going to use this constant of nature called the Planck's constant. This is really changing the way we think about metrology and the way we think about sensors. So just to highlight that, Boltzmann constant is how Kelvin is now defined. So if you want to make a measurement of the Boltzmann constant, sorry, that's done for now. We've got a digits as far as we need, and the uncertainty associated with the Boltzmann constant is 0 according to our system of units. And then what you do is you can use the Boltzmann constant to trace temperature. So now, if you go and make a measurement of a triple point cell, you can actually assign an uncertainty to that triple point cell. Same thing with the lump of metal in Paris, the kilogram. Before, if someone took a file and shaved off some metal, it would change the mass in the entire system of units, which is a little bit crazy, right? But that's not the case anymore. Now, because Planck's constant is the way to realize mass, the kilogram actually has an associated uncertainty with it. Okay, so Boltzmann constant and Planck's constant are the two things that we're talking about. So why is this important? It's important because, for example, the units of pressure, and I'm going to talk a little bit about that, is now linked. Pressure, you always need to know the temperature, and you also usually link it to mass. At the BIPM, there's something called the CCM, the Consultative Committee on Mass. Pressure is a Bragg unit. It sits within the CCM for mass. What is these redefinition? What have they done? They've now made pressure traceable to these fundamental physical constants. So now all we have to do is figure out how to make measurements of fundamental physical constants directly, and we have, in theory, a system of units that is now directly traceable to nature and doesn't need this calibration chain. So that's the nutshell of the idea. It's important because it democratizes the metrology system. In the previous system, if you didn't have a copy of the platinum iridium kilogram, you were out of luck. You had to go find someone that had one. The way nature works, anyone can observe it anywhere at any time. It works not only anywhere here on the planet Earth, it actually works anywhere in our solar system or anywhere in our galaxy. So it is really for all time and for all people. And you maybe expand it to all life forms as well. So why is this important? It also just changes things often to just a counting problem. So if you can just count things, you've made a measurement. Certainly the mole is an example of just a number, but it's an important number, so we have defined it as one of our units. There's some controversy around what numbers should be part of our SI system, but the mole being so important in chemistry is still there. The fundamental part of this, and the reason why this is so important, is that by using these physical laws and traceable physical constants, we have these intrinsically accurate sensors that don't require recalibration. Okay? So I think you've gotten a good picture of what we've moved to and from. So we've gone from a classical system and we've moved to a quantum-based system. So the question I will pose is, why is the quantum system better? Okay, so I got some slides. So here's a little thought experiment. Okay, classical SI versus quantum SI. So if you're using a classical model, and I'll draw your attention to this purple line here, and you're making an actual measurement. That would be the red dot with the error bars on it. What's the result that you're going to get? And the answer is anywhere in that pink band up there. So that's what you're going to get as the answer to your question in a measurement. Now let's change that model and now look at this quantum model. This quantum model over here has these discrete energy levels, say atomic energy levels, for example. Now we make a measurement with the same exact measuring device, and now what's your new result of such a system? Ah, look at this. Exactly the right answer. So your system, even though it had the same error bar, can now return a more accurate, more precise result. So this is the importance of moving to quantum-based sensing systems, because it really will enable us to do things that we haven't done before. So classical versus quantum. Classical, this is our summary. It's artifact-based. It's incremental improvement. Standards to calibrate the sensor model. So you need to have a standard out there to calibrate your sensor. And there's a chain of traceability running around. People with FedEx and UPS in the United States are big shipping, DHL, I guess, here in Germany. And they make a lot of money running around shipping things back and forth to the metrology lab or metrology institutes. And now, if we think about this quantum metrology, we're going to break the chain. We're breaking that chain of running around back and forth. We're looking at fundamental constants. It's really a transformative improvement. And this is what's, I think, so cool. It's a dual standard and a sensor all wrapped up in one. And this is what we've dubbed as the zero-chain traceability, or another way to put it is calibration-free, or another way to put it is self-calibrating. And those are slightly different things, but they all achieve the same result. Again, that end result is the fit for purpose for your particular measurement to make sure that your situation is being addressed in a way that lowers your risk for failure of the calibration system. Okay, so I'm going to take a few minutes now, and I'm going to ask the question, so how can you use light to measure pressure in vacuum? All right, so I'm going to talk about the fixed length optical cavity, and this is a snapshot of a paper that I was an author on. It's in Nature, and it talks about basically how we've moved from over 400 years of making pressure measurements with mercury barometers. And now we're going to do it, what? With a cavity and some laser light, and a couple of mirrors bouncing back and forth. And that's exactly what we've done. So on this slide, if you look over, you can see Evangelista Torricelli here. He invents the mercury barometer, 1643. And this is kind of neat because we've probably all done this experiment ourselves when we were kids in a bathtub. It's a bathtub, and you've got a cup, and you fill the cup up with water, and you pick the cup up, and you notice that all the water stays in the cup. Torricelli does this exact same thing. He does it with mercury, and he has a glass tube that's a meter long, and he fills it up, and he puts his thumb over the end and puts it in the bowl of mercury. And what he notices is there's this little gap at the top of the column. And no matter how long he makes the glass tube, when he fills it up with mercury, that same level always returns. And what he's basically invented is the measurement of atmospheric pressure, because atmospheric pressure is pushing down, and what he's measuring at the top of the column is a vacuum. So a lot of people think of Torricelli as being the guy that invented pressure, but he's also the guy that kind of invented vacuum. Because vacuum is very important to this measurement because all pressure measurements are differential by nature and have to be referenced to something. And what we call the absolute pressure measurement is a reference to vacuum. And your barometer just won't work if you've got air trapped in the top of your tube. You really have to have it pumped out at vacuum. So at NIST in Gaithersburg, Maryland, picture me standing next to what looks like a building column. That's actually a mercury manometer. It has a column on it that's 3 meters high. So it goes all the way up and actually partly out of the ceiling. scanners work incredibly well, and this one is one of the best in the world at a few parts per million accuracies in terms of its pressure readings. The problem with it is if you want to make a higher column manometer, you have to keep adding more and more mercury. It also has a lot of mercury in it, which is a toxic substance that you're trying to get rid of. So in 2018, we came up with this idea that you could take a glass cavity and you use laser light bouncing back and forth in this cavity to make a pressure measurement. I've got a couple of slides that explain how it works. But just to continue with this slide, what you're seeing is a transition from the artifact-based really over to the quantum-based. So in the artifact world, the pressure that you're going to generate is called rho GH. Rho is the density of mercury, G is the constant gravity, and H is the height. But now in the quantum-based system, it's the refractive index of the gas that's in one of the cavities, the Boltzmann constant, and the measured temperature. Boltzmann constant is fixed now, so all you need to do is make an ITS 90 measurement, because we're still using ITS 90 in the lab, and you've got your measurement of pressure. It's been pointed out that if you do happen to have another way to measure pressure, this also becomes a thermometer. So it can be used to measure temperature in the reverse. It's just a matter of what you know and what you don't know. If you know the pressure and the temperature and the Boltzmann constant, you can measure refractive index. So it's just a simple equation that allows various constants of nature to all be defined. The power of this technique, however, is that once we agree on a value for the refractive index of a gas, and you can calculate it very precisely for helium using quantum mechanics and get to a fraction of a part per million. So it has the ability to go lower in pressure than anything, or lower in certainty than anything we have today. Okay, so how does it work? So this is a two-channel cavity. Why two channels? Because one, we're going to hold at vacuum, and the second, we're going to fill with gas. So Fabry-Perot cavity is a cavity where you get a lasing condition when the cavity length is equal to 1/2 wavelength of an integer of the 1/2 wavelength of light that's in the cavity. So in this case, the bottom cavity isn't going to change because there is no change in pressure. And by the way, the definition of refractive index of a vacuum is 1. So if you look at that equation, wondering where the 1's coming from, it's the fact that it's referenced to vacuum. Remember I said all pressure measurements needed a reference to vacuum? In this case, it's very nicely defined in the math. And now all we do is we add gas to the top cavity, and what happens? So as the gas enters the cavity, the light in the cavity speed changes. So we all know what the speed of light is, and if you look it up, it always says speed of light, and then it says in a vacuum. Why does it say that? Well, because it's not in a vacuum, it's got a different speed. Another way to look at that equation is if it's got a different speed, it's going to have a different wavelength. So you begin adding gas to the cavity. Now the number of wavelengths is no longer fitting that integer number of 1/2 wavelengths that you previously locked to, so you're going to lose your lock signal. So all we have to do is cleverly vary the frequency of that input light to relock the cavity. And this can all be done very fast. And it's very, very precise in terms of how it works. I was so shocked when we did this experiment because we turned it on and we got to a vacuum. We actually had a vacuum gauge on it. We shut the valve on the pump and we slowly saw the pressure creeping up. 2 times 10 to the minus 7, 3 times 10 to the minus 7, 4. And the optical cavity was tracking the ion gauge. So that's how sensitive this technique is. It can really stare down in and literally count the number of atoms that are inside the cavity. That's what it's doing to get to the pressure. All right, so I've got a little animation that basically shows exactly what I said in words. So laser coming into that top cavity, it's filled with gas. You notice there's a pressure gauge on, and we've got this frequency of the cavity running. And so when I press the button, the gauge starts to go up in pressure. The beat frequency now is changing. And so what we're going to do when we actually make a measurement is we're going to not look at the raw frequency, which is megahertz. We're going to look at the difference in the frequencies between the vacuum cavity and the measurement cavity. And that's going to get us into the kilohertz range, makes it a much easier measurement to make, doesn't require any mercury. And a fixed length optical cavity is about this long in the one I just showed you. And that covers that 3-meter high mercury manometer, and does it with, in theory, it can be more accurate than the mercury manometer. It currently isn't, and the reason why is refractive index is currently the best number for nitrogen, which is what we want to use, is been defined by NIST, and we did it using the mercury manometer to measure the pressure to define that refractive index. So we don't need the mercury manometer anymore, and what's really cool is if somebody anywhere in the world makes a better measurement of refractive index, we can use it, you can use it, everyone can use it. And so anyone that has one of these devices, plugs in the exact same physical constants, now has the advantage of the best accuracy device. All right, so a new way to think about pressure. So in the classical pressure measurement, it's force per unit area. And it's literally something pushing on an area. This is how, like, a piston gauge works. It works well, but it is artifact-based. But now we're talking about a new way to measure pressure. And what's kind of cool, because my physics professor always taught me, if you want to understand nature, just look at the units, follow the units, and you'll get the right answer. Well, what's clever about the pressure unit, force per unit area, being defined as the Pascal, is that it also, if you just play with units, turns out that it's the equivalent of joules per meter cubed. So what's that? Joules are energy, and meter cube is just a volume, so it's energy density. That's what pressure is. And so I think it's really neat that when you start thinking about tearing down the world to its smallest pieces and seeing what's going on, in the case of pressure, you're just making an energy density measurement. And that's why temperature is always inexplicably linked to pressure, because it's also energy. So pressure is just another way to express energy, but in a very useful way. That's why just about every process uses pressure in it. All right, so where are we at today? NIST has been working with an industrial partnership in something called a Collaborative Research and Development Agreement. And this picture is courtesy of MKS Instruments, which has made a cavity that's about this big. So bigger than a sugar cube, but much smaller than a 3-meter mercury manometer. Okay, so I'm going to shift gears now, and I'm going to talk about, well, what happens if you want to measure pressures, say, below 1 × 10⁻⁷ torr? Well, it turns out we've got another method for doing that, and what it is the cold atom vacuum standard. So there's a Nobel Prize-winning physics was done at NIST in 1996-97, which happened to be about the same time I joined NIST. I had nothing to do with that Nobel Prize, I'll add. However, once I got to NIST, it seemed like the Nobel Prize has started coming. So, you know, that's a good correlation. We'll see if I can make good use of that. What's the blue arrow pointing to? It's pointing to a cloud of magnetically optically trapped lithium atoms. About 1 million of them, and what they're doing is they're fluorescing. You can see this with the naked eye. I just held my phone camera up to the chamber, snapped the shutter to get this picture. How does it all work? Well, I'm not going to go into explaining how you can use laser light to trap atoms. I will talk a little bit about how this particular device works, but before I get into it, I'm going to do another quick thought experiment. This is, why do you care about really low pressures? So in surface vacuum metrology, there's this unit called the Langmuir. What is a Langmuir? Well, it says that at 1 × 10⁻⁶, if all the gas particles in your system will stick to the surface with a sticking probability of 1, a Langmuir will occur in 1 second at that pressure. So it means that in 1 second, at 10⁻⁶ torr, all the atoms, say in a square centimeter, there's about 2 × 10⁻⁵, say, atoms of nickel. So 2 × 10⁻⁵ atoms are hit at 10 to the minus 6 torr. So what happens if you go to a very much lower pressure? Let's say you go to 10 to the minus 12 torr. That's almost impossible to measure, by the way. If you get an ion gauge, you won't know if it's really accurate at that pressure or not. But what's going on at the surface chemistry at that point? It amazes me when I did this, but it's there in the math. You're still getting 1 billion collisions per second over that 1 square centimeter area, even at 10 to the minus 12 torr. So this is why if you're in a semiconductor fab or something like this and you're really worried about your process control, a better vacuum measurement is actually very useful. The problem is we haven't had a way to even measure it before. Now the cold atom trappers, they figured this out when they were making their traps. These Nobel Prize winning physicists realized that they had to get their vacuum better and better and better. Why? Because the trap lifetime was dependent on the pressure in the chamber. Why is this? The atoms in that trap are actually at a few microkelvin in terms of their temperature. And if you have a gas molecule flying around in the chamber, it's actually about the temperature of the walls of the chamber. At room temperature, that's like 300 K. So what's happening is these hot red background gas molecules, in this case we're simulating hydrogen, are going to come in and they're going to knock out the atoms in the trap, and your trap's going to go away. So decay of the trap is going to be dependent on the pressure. So here's an animation showing that when we turn on the 2D MOT, it starts to glow, and you can actually see it with your naked eye. And when you turn off that 2D MOT trap, it dissipates. And it's that exponential decay that you're seeing there that becomes your pressure measurement. So again, you're just using a regular CCD camera. In fact, the camera in your phone is good enough to make this kind of measurement. And it's just really amazing that you can do that. You're basically measuring the pressure, in this case, by watching individual lithium atoms be knocked out of the trap. Again, just a counting problem. A very different way to approach your metrology. Well, so how do we take this lab-scale device and make it into something that's much more compact? Well, it turns out that the group has been working on this, and they built some models. And at the center of this model, you can see, it's a little bit hard to see, but right in there is this special chip. What's that chip doing? Well, in order to make a cold atom trap, you normally need a bunch of lasers, one going this way, one going this way, one going this way, one coming up from the bottom. So all these different lasers, what they're doing is the photons are basically using the Doppler shift of the moving atoms, cooling them and trapping them into the center of the trap. All those lasers is bulky and expensive, so what the team figured out is they could make a diffraction grating. They cut a hole in the bottom. They actually diffuse the lithium from underneath, so that's what the blue balls are, the lithium coming up from underneath. And then they bring a laser in from the top down onto that grating. And what happens is that grating interferes with itself in a way that basically makes up for all the other lasers. So now instead of having this whole gaggle of lasers around your thing, you're using one laser shining down onto this one device. Well, how big is it? And does it work? Okay, so here's a little video. What you're seeing here is I'm looking in the chamber, and this is the cloud of lithium atoms being trapped. And I'm going to play the video, and you're going to see it sort of wink in and out right there. And the reason for that is we were pulsing the magnetic field because we didn't have water cooling on our magnets, and we didn't want to overheat things. But it works incredibly well, and again, you can see that with your naked eye. How small is it? Here's Steve Eckel. He's the PI on the project. He was at a conference last year in the United States. What he's doing is holding a conventional ion gauge in one hand, and he's holding the cold atom vacuum probe head in the other. So aside from the lasers, we've got this down to basically the size of the existing technology, and it would not be that difficult to improve upon the laser systems to make it better. But that is kind of the direction we need to go for these things to get down to chip scale. You're going to have on-chip photonics and so on. So let's see, how am I doing on time? About another 20 minutes? Yeah, okay, perfect. All right, so I'll talk a little bit less about this. So we've talked about how to measure pressure and how to measure vacuum. What about temperature? Well, temperature is an interesting one. The spoiler alert here is this is not quantum, all right? This is not going to measure Boltzmann's constant or be referencing to Boltzmann's constant, but it is going to replace something called the platinum resistance thermometer. So the ITS 90 scale relies on a platinum resistance thermometer that is how you transfer the entire temperature scale. What we have here, and shown at 3 different size scales, is the 1 millimeter is actually the chip being contacted to the thermometer, and then the 2 micron scale shows a little bit more what's going on, and then at the 500 nanometer scale, you can see that what you have is this little channel with a bunch of little holes in it. Now, what is this? It's actually just a photonic crystal. It's just like the optical cavity. If you get an integer number of wavelengths in this little waveguide, you will actually get a resonant peak. What's powerful about this technique, it's all made out of silicon. So silicon's a very good spring. It also can be made really small. And when you change the temperature of this, because the expansion of the elements occurs, it changes refractive index, and this is how you make a measurement of temperature. So it's very analogous to how the flock works. And in fact, we're currently working on how to take the same photons that we would use for the fixed-length optical cavity and put it on a sensitive optical thermometer and get a readout of the temperature as well. The advantage of the spot thermometer is that it is way more stable than the traditional SPRT in terms of what it can do. The classic SPRT, or standard platinum resistance thermometer, if you drop it or tap it or anything like that, the grain boundaries can change inside the platinum wire, changing the resistance and therefore changing its calibration. What we've seen with the silicon photonics thermometer is that it doesn't have any of those problems. We think that this thermometer, once characterized at the beginning of its life, could be demonstrated to never needing recalibration again. So while it's not primary in the sense of direct looking at quantum, it is awesome in terms of what it can do for fit-for-purpose field calibration going out in the field and not needing to return back. In terms of the technology and how small it is, here's a picture of a human hair, and here's a picture of a photonic thermometer. And if you shrink it down and place it in relation to that human hair, what you're going to see is that you could fit over 1,000 thermometers on a single human hair. So this is a case where the actual sensing element is definitely chip scale, but again, the readout is going to be something bigger. It's going to be, right now we're looking to basically find a platform that will replace existing platinum resistance thermometers. And this will be useful to calibration standards labs early on because they can use the spot in place of the platinum resistance thermometer as a drop-in. And once it's demonstrated to have even better long-term calibration histories, we think it'll take over. Okay, so very quickly, I'm going to talk about measuring mass with the Planck's constant, h. So as I mentioned at the beginning, we're moving from this platinum iridium block of metal to this laboratory scale device that's called NIST-4. And this piece of apparatus was actually used in that 5 years ago when Planck's constant was defined. Actually, last year, Stefan Schlaminger came to the conference. He's one of the folks on the NIST team that has Planck's constant tattooed on his arm, out to all the digits. And it was using this device that they were able to do it. Now, that's a very big device, but what has the NOAC program been doing since? We've been trying to figure out how to make it smaller. So we've got a tabletop kibble that's maybe this big, and then we've got a generation 2 tabletop kibble that's now maybe this big. So it is getting smaller in size. The US military is very interested in this, and in fact, just last month, we delivered the first working version of a tabletop kibble balance for them to use in their metrology chain to prove it out to see if they can break this shipping of masses back and forth. They have a primary standard sitting right there. All they need to do is calibrate all the inputs, and they've got it worked right out. Okay, so moving along, as you can see, there's a lot. Oh, you want to? Yeah, we can go back. There we go. Yeah, so all these different balances, it's just a matter of shrinking things down in size. I won't have time to talk about it, but I'll just mention it. This guy right here, electronic torque realizer. So they realized that they could actually make a measurement of torque using the Kibble principle. And this turns out to be incredibly important for like calibrating torque watches and torque screws. So like when you literally tighten a lug nut on a wheel or something, you're using torque. Well, this is basically an electronic way to measure torque in the, I'm sorry for the units, inch-pound range. So very low pressure, very low amounts of force in torque. But what's beautiful about this technique is that when you over-tighten it, it doesn't break anything. It's not mechanical. It's a clutch. It slips under the electric field and relocks and goes right back. So, and the Air Force is currently working to get some of these deployed into their lab in the very short time frame. The last example, and then I'll move into some of my wrap-up notes, is radiometers in space. So if you put a radiometer in space, this is an example of something that is never going to come back. It's gone. It's in orbit. And so you really do want technologies that are stable. In this case, they're using a GPS signal to make sure that the voltmeter isn't drifting. And so this idea that a lot of our calibration drift can be traced back to a frequency standard drift is an area where you can very easily with GPS take advantage of this right now. So all you have to do is look at your instrument, figure out why it's drifting, and anywhere there's a frequency drift that's occurring, use GPS to correct it, bam, you've just fixed that part of the calibration drift. All right, so what makes a sensor? I think this is really an interesting question, but if you really strip it all down, it's just a way that it can communicate unambiguously what it senses, and it can communicate that information to a person, which is what we're used to, but it also could be a machine, so think AI, right? Or it could just be communicating with another sensor. So it really is sort of the secret of how you make more complex things work. And if you look at like how the human body works, it's also a buildup of neural networks, which are sensors that are talking to each other. I think there's something like 10,000 pressure sensors in your foot, in the human foot, designed for feeling what you're walking on. So the idea that if you're going to build a complex system, you're going to need a lot of sensors to do it. And it's certainly important that you can trust these sensors in a way that your system won't have a failure. So I have one video left, and then we'll wrap up with questions. Audio folks, this is your wake-up call. We're going to the video.
High-risk research is a way of making science fiction a reality. We have at NIST the ability to look long-term. And this is something that is getting more and more difficult to find in U.S. industry.
I think it's important for the government to do this work because no one else will. I think there's a pretty wide gap between the academic research and industrial manufacturing of a new product.
We have over 100 years of expertise creating measurement tools that help industry bridge the lab-to-market gap. NIST-on-a-Chip is about shrinking those tools to the ultra-precise quantum level.
Because we look long-term, we can take risks on things. We can try things that are unusual. And also we have a lot of innovative people that spread a broad range of scientific backgrounds. That's really important for NIST-on-a-Chip. It's very interdisciplinary.
I'm not aware of any company that would have that depth and breadth to be able to address all these different measurements. There aren't too many places like NIST where you have some 3,000 scientists working across all these disciplines focusing on measurement.
This type of vision is one that I think you can only really bring to fruition in a large national metrology lab, because you really have to make sure that you have that traceability back to the standards that are required to make a proper, accurate, and useful measurement device.
We're talking about technology that is truly disruptive. Ultra-precise measurements, anytime, anywhere. It will enable industry to create a host of innovative products we are just starting to imagine.
Okay, so it brings me to sort of our wrap-up notes. I've got like 4 or 5 more slides. But I think it's just important to sort of take a step back and see where, we call it NIST-on-a-Chip. There are metrology labs around the world, PTB, for example. And we actually see this as being a trend across more than just what's going on at NIST. This is really an international effort in terms of what we see. And it's all being driven by this redefinition of the SI and the fact that we now can link to these physical constants. The power that we see is linking these technologies and these quantum-based systems to nano-manufacturing so that you can make a lot of them and make them cheaply. The concept of quantum 2.0 is sitting right here as well. That's the ability for us now to engineer systems to get the type of measurements that we want. And when you put that all together with Industry 4.0, which is machines talking to machines and AI, we really do see this entire system as not only being possible, but is probably just going to accelerate very quickly once we get going. And I think you saw today some of the examples. In terms of the NIST-on-a-Chip program, we have over 18 projects in 11 different technology areas, and with over 60 different technology outcomes with commercial potential. Some of the devices are shown here. I talked about the pressure refractive index, the vacuum, the chip scale atomic clock, temperature, kibble. Didn't have time to go into Rydberg sensing, but it turns out you can make very precise measurements of electric field by using Rydberg atoms. If any of you are lucky enough to get out to NCSLI in Denver, we're actually going to have Chris Holloway, who's invented this device. He can live stream video over the Rydberg atoms and use lasers to pick up the image. So we'll have a camera facing in the audience, and you'll literally be able to see yourself on a signal that's been transmitted and received by Rydberg atoms. It really simplifies the electronics, and it's actually going to be cheaper than the electronics that we're using today. And DC voltage and power sources are also some of the other applications. Because I'm running out of time, I'm not going to belabor this, but it's important to really understand what does this mean for the National Metrology Institute. I'm part of a committee in MECO called TC25, and we are currently looking to answer this kind of question because we understand the importance of quality systems in maintaining something that has zero-chain traceability attached to it. We really don't want to see a collapse of the quality system just because we've now broken the measurement chain. So it means that while we've solved one problem, we've created another. This is what we do as we become more clever. In terms of where we're going next, it's really about taking advantage of new quantum properties to create intrinsically accurate sensors that beat that conventional noise limit. We see applications in pressure, vacuum, gravimeters, accelerometers for navigation, and this is incredibly important in things such as GPS-denied environments. What's needed to make this work is scaling of critical components, integrated photonics like on-chip lasers, proving out new physics, and a new metrology culture is part of this as well. What we need at NIST and at other NMIs are really commercial industrial partners to come in that say, hey, we would like a piece of this action. While NIST and others can sort of demonstrate and de-risk the technology, ultimately getting it into the field is going to require the incredible manufacturing capability that industry has when it comes to putting these devices out in the field. So with that, I'm thanking my co-authors, which you see up there on the screen, and many others that also aren't on here but are at NIST that have worked on a lot of the work that you see presented today. And with that, I would like to thank you for your attention. And if time allows, I would be happy to answer any of your questions.
Jay, thanks a lot for your fantastic talk about the fundamental constants and how to work on them, with them to bring these fundamental constants to us and also to the industry. And that's, I think, a very important thing, because we have also heard today that it is quite a real big problem if you are in the process industry and you have to stop the whole process because you have to calibrate.
Exactly.
Yeah? And concerning the kibble balance, we are just working also on such a thing, and we know that the pharmaceutical industry is very interested in this. So once more, the pharmaceutical industry may be one of those stakeholders which may be the first of interest. What do you believe about this?
So what was the question?
What do you think about pharmaceutical industry for these things?
Absolutely. I mean, anytime you can reduce those long chains of moving masses back and forth, you really are simplifying the process. What's really powerful about these kibble balances, the NIST team, and I imagine you're probably seeing the same thing as well, turns out they work really well down even at very, very low masses. And certainly that's where, you know, in the drug industry, you're measuring out milligrams. You really do want to have a good uncertainty associated with something. So absolutely, I think the medical industry is probably a first adopter. The military, they're cagey about why they want it, but basically, again, it reduces, in the case of the military, they see calibrations as a maintenance problem, you know, and so what they're trying to do is make this problem go away. In the case of the pharmaceuticals, I imagine that they are also looking at it from a quality system, and mass metrology just requires a lot of transfer standards.
Yeah, thanks. But before all the others leave, are there any questions from the auditorium? No. So
I will be around if anyone wants to come up and talk to me.
Okay.
So,
so thanks a lot once more for this grandiose talk.
Thank you.
I'm very, very happy that we are able to describe with only 7 fundamental units the whole world, and if we are able to touch them by doing this in this way, it's fantastic. And so maybe we can retire all the NMIs afterwards.
We'll come back when we have all those sensors installed in the chemical factory,
Yes.
right?
Okay.
Okay, thank you.
So thanks a lot.